Electromagnetic radiation is radiant energy composed of oscillating electric and magnetic fields. What does it mean to oscillate? Okay, waves. Yes? So, what is electromagnetic radiation? We have visible light, we have radio waves, X-rays, gamma rays, ultraviolet, infrared. Microwaves didn't make it into that list, but they're also in there. Okay, those are all types of electromagnetic radiation. Just like electrons, electromagnetic radiation is both wave-like and particle-like. Yes, it's both a wave and a particle. And a photon is a unit of electromagnetic radiation or light that has a quantum, which means fixed amount of energy. Yes? Are you going to have to be able to explain this? No. You're going to have to be able to use some formulas, okay? So this just talks about wavelength. We have not yet mentioned amplitude because we don't do any calculations with amplitude, but amplitude is the distance from the node to a crest or the node to a trough. Okay, it's the vertical distance. I don't know that you need to know it for chem. I don't think you do. So we're just going to leave it at that. Okay, that's your amplitude. Common units, nanometer, 10 to the negative 9 meters, or angstrom, just so you get used to seeing that unit because it will come up from time to time. It's an A with a little 0 over it or an O over it, and it is 10 to the negative 10. Okay, so we have nano, 10 to the negative 9, angstrom, 10 to the negative 10. I don't think you're going to come across angstroms in the AP exam because they give you all the prefixes. So I imagine they'll give it to you in nanometers. Yes? And if they do give you angstroms, they will probably tell you it is 10 to the negative 10, right? Because that's something that they have not said you need to memorize. Okay, all electromagnetic radiation travels at the speed of light, which is represented by the letter C. And do you guys know the value of the speed of light? 3 times 10 to the 8 meters per second. So that's the nice round number, 3 times 10 to the 8 meters per second. That's fairly easy to remember. The value that you are going to get on your AP data booklet is 2.998. So we have 4 sig figs times 10 to the 8 meters per second. So if you're doing a calculation, please use that one. Yes?
So all of them travel at the same speed of light?
All of them travel at the same speed.
But they have
different wavelengths.
So this would mean that some of them technically travel like more distance.
Okay, this is me being a chemistry teacher trying desperately to understand physics because I don't really understand physics. Okay, so are you taking physics?
Yeah.
Yeah. Ask your physics teacher because they'll give you a better explanation. This is how I think of it, okay? Waves both travel at the same speed. Yes?
Yeah.
That's how I think of it. Yeah? Except for a lot faster than that. Okay, so we have speed of light is equal to the wavelength times the frequency. That is one of your formulas on the AP data sheet. anytime you have two variables on the same side of an equation, they will be inversely proportional. If one of them goes up, the other has to go down, because especially here, because this is c is a constant, right? Speed of light is a constant. So if you make lambda bigger, in order for it to still equal the speed of light, then the frequency has to be smaller. Does that make sense? Okay. Okay. So we're going to do a practice problem here, and I'm going to do it from scratch. Over on the side, it's all worked out for you. So if you want a piece of paper to do it from scratch along with me, grab yourself a piece of paper, or you can just look at it on the sheet. We want to find the frequency. So when you're setting up a problem like this, I don't know how you do it in physics, but I imagine that your teacher tells you to write down what you have and what you want to find. Yes?
Seems actually much more.
Ha. So my frequency is what I don't know. What's the unit of frequency? Seconds to the -1 or hertz. I think this one asks for it in hertz, but I'm not sure. We have a wavelength of 750 nanometers. And we have a formula that relates those two quantities, right? We can go to our data pages and say, oh, what's the formula that relates wavelength and frequency? C is equal to lambda nu. Okay, wavelength times frequency. Oops. So we have C is equal to lambda nu. Now, if your physics teacher is anything like I suspect, they will probably say solve your equation before plugging in the numbers. Do your physics teachers tell you that? Yes. So let's keep doing that. So we want to solve for frequency. Okay, and hopefully, so everybody solve for frequency. I want to see if your algebra skills are up to it, just in case. Okay, you should get that. I don't care how you get it. I don't care what method you use to do your algebra. You don't have to show any work because it's fairly straightforward algebra, but that is what you should get. If you got something different, come and see me. I got some like little algebra boosters. Okay, so if you're like, oh my God, what happened? I forgot all my algebra over the summer and I'm not taking physics yet. If that's the case, come see me. I do have some little algebra worksheets. Okay, so we have this, and then we plug in our values. So we have C, which is 2.998 times 10 to the 8. 2.998 times 10 to the 8 meters per second. So I'm going to say meters seconds to the -1 because that just makes it tidy for me. Okay. One of the reasons that they like to use the seconds to the -1 rather than per second is because when you've got like a whole thing on top of another thing, otherwise you end up with this over this over this over this, and it gets quite vertically big. Okay? This way all your units can be on one line. But it's up to you if you want to write meters per second like that, that's fine. Our wavelength, can I do this? Will that work? Yeah, why won't this work? Because here I have nanometers and here I have meters. Those will not cancel out. I want to cancel out and get seconds to the -1. Yes? So I need to convert 750 nanometers. And if you remember, what is nano equal to? It's equal to 10 to the +9 or -9? -9. So we're just going to replace that nano with 10 to the -9 and put in meters because it's just easier. You can put it into scientific notation if you want, but you don't have to. So this would be divided by 750 times 10 to the -9 meters. Because this is chemistry, you absolutely do have to show your units. Okay? There are reports from the chief reader, who's like the head marker of all the AP tests. And one of the common comments that comes up is students must show their units in their work, in their calculations. Okay? So I don't know what it's like in physics. You would want to go and read the chief reader's report for physics. I've never taught it, so I have no idea, but definitely in chemistry, they're all about that, and we can show. What is wrong with this stupid line? No, you have to apply for it, and like it's competitive, and like I don't know. I'm like, I don't know. I like spending my summer just goofing off and not marking things. Although I don't actually goof off, because what did I spend my summer doing? I spent it moving all that assignment from Schoology to Teams. It was super fun. Anyway, here we go. We chug that into our calculator. You guys know the expression plug and chug, right? Do you know the expression plug and chug? Plug and chug. So you get your formula in the manner that you want it. You plug in your numbers with the units, and then you chug through the values on your calculator. Plug and chug. So 2.99 E8 divided by 750 E -9 equals 3.986 repeater times 10 to the 14. And my unit, the only unit I have left is seconds to the -1 or hertz. So now we need to put this to how many sig figs? Let's see, what is the 750? Honestly, I feel like this would be like 750 dot. Do you know what I mean? Like I feel like that's what they meant. So we're going to go to 3 sig figs. They will probably, is the answer to 2 sig figs? I don't know. Anyway, AP will be more obvious than that for you. They'll probably give you something like 754, so it's not unobvious. Okay, so if there was a dot there, it would be 3 sig figs, and so that would then become 3.99 times 10 to the 14. You can leave it as seconds to the -1, or you can write hertz. Either one is fine, and you're done. Box your final answer. Are we good? Okay. Now, the energy of a photon, we have another formula for that. It is related to its frequency by Planck's constant, h. So in this case, h is the constant. And you'll notice that E and nu are on opposite sides of the equation. If things are on opposite sides of the equation, are they directly or inversely related? Directly. So if 2 variables are on the same side, they are inversely related. If they're on opposite sides, they are directly related. Because if energy gets bigger, then in order for that to remain equal, the nu value also has to get bigger. H is given to you on your data sheet. The unit is joules times seconds. So if we want to solve for frequency, actually, you know what I'm going to do? I'm going to do it over here. So we have E is equal to, no, you know what? Never mind. We're going to go here and do this practice problem. Okay, this is on the next page. We'll come back to that later. What is the energy of a photon having a wavelength of 620 nanometers? So we want to know the energy. What? We're on page 29. Or sorry, 30, page 30, top of page 30. Now, what? Yes. So here's what we're going to do. We're going to do it first using the two separate formulas, and then second, we're going to put the two formulas together. I don't know why, but the only one of all the formulas I can remember is the one that's not on the data sheet. All the other ones I get mixed up on. But anyway, here we go. We want to find energy, and we know that wavelength is 620 nanometers. What should we do with this value? Change it into meters. So that is 620 times 10 to the negative 9 meters. So if we want to find energy, the formula that we need is E is equal to h nu, which means we need nu. Yes? But we also know that C is equal to lambda nu. So we're going to start with this, and then we're going to go to our second equation. Yes? So let's solve first for frequency. Frequency is equal to C over lambda, just like we did last time. We have 2.998 times 10 to the 8 meters per second over 620 times 10 to the negative 9 meters. 2.998 E8 divided by 620 E9 negative equals 4.835 times 10 to the 14. Meters cancel out, and we're left with seconds to the negative 1. Now that we know our frequency, we can plug it into our second equation, E equals h times nu. And the h value is a constant, so let's go look that up. It was, h is 6.626 times 10 to the negative 34. 6.626 times 10 to the negative 34, and the unit is joule seconds, and I've not left myself enough room here, so I'm going to say times 4.835 times 10 to the negative 14 seconds to the negative 1. Yes? Where did Planck's constant, how did they find it? That's a good question. I have no idea. I can go look into it, or you can Google it probably as easily as I can. I'm sure they would have measured energies of light and frequencies of light and found out what the ratio is. That would be my guess, but I don't know how they would do that. Okay, let's look at our units. Seconds times seconds to the negative 1. Those cancel out. Are we okay with those canceling out? Right? Because that means seconds times 1 over seconds. Okay? So those cancel out. And the only unit we are left with is joules, which is good because we want energy, which is in joules. So we have times 6.626 E negative 34 equals, and we have 3.204 times 10 to the negative 19 joules.
Oh. So that's
And we want 3 sig figs. Let's just say it's 3 sig figs. 3.20 times 10 to the negative 19 joules. Why is that number so small? That's the energy of a single photon. Okay, just one photon. One photon is very, very dim. Okay, just one photon. At some point, you might be asked about moles of photons. Okay, in which case you're going to have to use 6.02 times 10 to the 23. Okay, but we'll get there. Now, this seems like a lot of work to me. Yes? Chugging around, blah, blah, blah. So here's what you can do instead, should you so desire. We're going to take our E equals h nu, and we're going to take our C equals lambda nu, and we're going to solve for nu, which is equal to C over lambda, and we're going to take the nu and replace it with C over lambda. So what we get is E is equal to HC over lambda. So you can derive this on the fly during your test or quiz or worksheet or whatever you're doing. Or, like I said, for whatever reason, this one sticks in my head. E equals HC over lambda. Just say it a lot of times, it'll stick in your head too, probably. E equals HC over lambda. E equals HC over lambda. Equals?
So it's just two constants multiplying.
Yeah, so you've got 2 constants on the top, and then you've got lambda on the bottom. So we would then have 6.626 times 10 to the negative 34 joule seconds times 2.998 times 10 to the 8 meters times seconds to the negative 1. The seconds and the second negative 1 cancel, and right now we've got joule meters on the top. On the bottom, we have 620 nano is 10 to the negative 9. Whoops, why did I write 19? 10 to the negative 9 meters. And now our meters cancel out, and the only unit we are left with is joules. Okay, so I don't care which way you do it. You can use the 2 formulas separately. You can memorize this formula, or you can derive this formula using both of them and then use it. Up to you. Is good? Okay. The electromagnetic spectrum, this is according to the reviews box, it says it should be remembered in terms of the energy ranking. Memorization of specific wavelengths or frequencies is not necessary, but you should remember the order of decreasing wavelength or increasing wavelength, okay? Now, how important is it for you to know all of these? Probably not. Like, do we really care if you know that gamma rays are more energetic than X-rays?
They are?
Yeah. Probably not. Should you know that gamma rays and X-rays are higher than ultraviolet? I think so. Like, I think that's something that might be useful. Should you know that anything below infrared? I don't think they're going to ask you anything below infrared. Oh, they do sometimes ask about microwaves. But, like, there's been one question that relates to the fact that microwaves are at a lower energy than the other ones in the last 15 years. So, like, if you think it's important to know the entire spectrum in order from, like, gamma to radio, You can spend your time memorizing that. You should know these ones. Yeah, for sure. And I feel like we could toss X-rays in there too. Okay, because X-rays are also used. Do you remember how we can bump electrons up? Okay, we can bump them up using UV light. We can bump from level 1 using UV light. We can bump them up from level 2 using visible light, or we can bump them up from level 3 using infrared light. If we use X-rays, we actually usually end up ejecting the electron altogether. It just gets ripped off the atom. And we're going to be talking about that in section 10.4, perhaps? Pardon me? No, it's not bad. It's how they determine the electronic configuration of atoms. Okay? Did you have a question, Brian? Yeah.
I was solving one of the questions. I was so confused because it said radio waves, but I didn't know it was like 2 meters, over 2 meters long. So
Yeah.
2 meters.
Yeah. So you should know that visible, just because it's handy to know, what is the spectrum of, what is the wavelength of visible light? What 100 to what 100? You go home and you do homework from 4 o'clock until 7 o'clock. Yeah? And then you have dinner at 7 o'clock, and then maybe you do some more homework later, okay? Visible is from 400 to 700 nanometers. I would know those, like, not that they're going to test you on it, but it's just kind of nice to have in the back of your head so you don't have to think about it too hard, okay? This is the emission and absorption spectrum, which we spent a fair bit of time on yesterday. So we're not going to spend a lot of time on it. If you take white light and you throw it through a prism, what do you get? You get a... If you take white light and you throw it through a prism, you get a rainbow. And this just kind of talks you through the whole process we talked about yesterday. Do you remember that demonstration the guy did with the discharge tubes, and then we saw the diffraction, right? So this is what they're talking about here, that high voltage is applied to hydrogen gas, and the electrons are excited, okay? And then the excited hydrogen atoms relax to lower energy states, and that's when we get an emission spectrum. So here we have our voltage. Here we have some H2 gas in the tube, glass tube. Out comes some light. And there's 4 different kinds of visible photons. Okay, so we got that 656, we got the 486, we got the 434, and the 410 nanometers. Is good? Okay, so that's our emission spectrum for hydrogen. Now we come to absorption, and if you remember absorption, we throw white light at it, right? This is all the colors of the rainbow, all wavelengths of photons. Yeah. Yes?
The speed of light, is it when it goes like this, or is it like the relative speed of the speed of light?
Speed of light.
No, like,
So they're all going at the same speed.
isn't there like 3 models of light?
Probably.
Like wave one. What if they red and mine are
Yeah.
the same distance?
same time.
Yeah. Red and violet go the same distance in the same time. So you'll have more peaks passing a certain point per second for the violet than you will for red. Yes?
Do like all sorts of like shit, like all the way from gamma rays to radio waves, all of them.
They all travel at the speed of light. Every single radio waves travel at the speed of light. Gamma rays travel at the speed of light. So actually we could toss that back here. They all travel at the speed of light. Yeah. Probably not, because that's more physics than chemistry. Yeah. I don't know. Talk to your physics teacher about that stuff. Because honestly, my knowledge of waves only goes like this far. Yeah? Okay. Absorption spectrum. So we have all the different photons. The hydrogen absorbs for specific wavelengths. And so all the light comes out except those 4 specific wavelengths. All wavelengths of photons. So all the colors come out except those 4 wavelengths. So these appear as black lines. They're the same. It's just that we have black lines on a rainbow. And the other one, we have rainbow lines on a black background. So here we would have colored lines.
Because the hydrogen is absorbing those lines.
Yes.
Oh,
So only 4 wavelengths of light come out because hydrogen only puts them out. Yes?
How many sig figs is the wavelength of light that hydrogen forms? Is it always like exactly?
I would say 3 sig figs.
So it's always like 6.
Yeah. Yeah. Okay. Don't move. I'm going to give you your homework. Your homework is these exercises on pages 35 and 36 and 37. Give them a try. I'm going to come back there and answer your question.